Okay, so in this presentation, as I always do, just to give an overview of what we have been working on and also the future roadmap. Okay, so as it's working. No, you tried that one, right? Huh? Good. Yes, let's change.
I'll swap the back.
Okay. So as many of you know, we are in an exciting phase of the exaflop kind of systems. Fugaku came, and then after that we have the. Still, this one is also not working. Yeah, I think. So then we have the frontier is on the top. But just to follow up Dan's talk, as you know, these days we are talking about all AI. We started with HPC and AI, but gradually you see there is also the big data. This is a new kind of a convergence which is taking place to not only provide solutions for the HPC, but also machine learning, deep learning, big data. So in fact, in our MVAPICH project, I'll try to show you, we are steering also a little bit in a different direction. Not only will we be able to just MVAPICH is only for MPI, but MVAPICH is also for machine learning. MVAPICH is also for big data. So I'll try to show how we are designing these stacks. So this is I'll try to provide a very brief overview of the MVAPICH project, then very quickly go over some of we have a lot of releases and how we are building actually that converged software stack here. You will see we have a high performance DL, MPI for QML, MPI for Spark, MPI for Dask. So we are trying to bring all these upper level middlewares as the MPI as the common substrate. So once you have a MVAPICH running on any system, everything else will run automatically, and it's performance portable, so you don't have to spend a lot of time on designing each one of these stacks. And then I'll go into some of the upcoming features. So as many of you know, I mean, here we are in the MVAPICH project. Those of you who are not familiar, we started this project almost day one of Infiniment. Infiniment was introduced in October 2000, and we were ready almost on the very first day when it came out. Prior to that, we were working on Mirinet, Quadrix. So we had our first actually open source design being demonstrated at Supercomputing 2002 in Baltimore. At that time, it was even a struggle to have just 8 nodes running with Infiniment. And now I think we have come a long way. People are deploying 8,000 nodes and 16,000 nodes. And we have a long partnership with Mellanox and NVIDIA working there. And I'm very proud of my team who have been working, as Dan said, like a 3 generation of students and staff have been working. So we are 22 years and counting. So now it is being used by more than 3,000 organizations in 90 countries, and just last week we crossed 1.7 million downloads just from our site. Okay, of course it's a part of SPAC, OpenHPC. Those we don't keep track, the vendors distribution stack. So these are directly from our website, and of course we have been empowering a lot of top 500 clusters, and as Dan indicated, we have been working very closely with them for 17 years. So this shows, as you can see, how the release time download, and we are in a very steady upward stream. So what we have done, this is kind of our software architecture kind of things. Here you will see all the different networking technologies. Even though we started with Infiniment, now we support all the networks, all the different multi-core, many-core systems. So in the top, we started with MPI, then PGAS. We have hybrid MPI PGAS. But actually now, there's a lot of focus on going on top to provide support for DL, ML, big data, data science. I'll talk more about that. But the biggest thing is this. These are our designs. So when we have the students, they actually go and then look for the newer problems, newer architectures. We come up with the solutions. We publish these papers. And then in 6 to 8 months' time, we actually take it to the production quality software. And yesterday, Hari mentioned about this, our QA kind of things. We have very nice test bed inside the lab. In fact, even we operate like a half research, half industry kind of thing. So we go through very rigorous testing. Even all the students get involved, and the staffs in the testing and all, and then we push it into the production. Even our a beta, alpha, RC1, RC2 also go through a lot of testing. So then let me go over this some of the recent releases. Our MVAPICH 237, that is the the most production quality release. That is the 2.3 series. It has a lot of features, support all the different networks like Rockport, Craze, Mellanox Sharp integration and all, and I'll show you some of the performance numbers. So that is still, we recommend. We have a new series 3.0, which is coming out or has come out, but not the RC release yet. So here, if you see, like these are some of the highlights of the 2.37 GA. We have like optimized, continuously we optimize as the processor architectures are changing, network speeds are changing, internode, intranode. The SARP support, we have done a very tight integration, and also MPI with Samir, we have been working very closely, and also newer adapters. We have started supporting like the Broadcom, Rockport, and Slingshot. So these are like the standard Infiniment. If you take a look at like the AMD Milan and STR200, we do very, these are the intra-node performance, like around 190 nanoseconds. We give core to core. And here also like around 1.8 microsecond, we give like a internode performance. We have done like a tight integration with SARP. These are actually from TAC Frontera, Dan mentioned. Here you will see like our MVAPICH 2X version, which has advanced support. Like with the SARP support, we can actually give you very much improvement in terms of the collective performance. Now, recently, there's a lot of work going on in terms of the non-blocking collectives. Most of you, traditionally, people have used only blocking collectives, but as you know, the system becomes larger when you are using blocking collectives. You are not able to exploit overlap of computation and communication. So even from the pure host side, we have been optimizing all these non-blocking collectives, and gradually application people are seeing the benefits of non-blocking collectives so that they can rearrange their applications. And then, of course, with the new DPU technology and all, you can actually offload. We saw some of those examples yesterday from the XClub solution side. We have how we have converted the MVAPICH 2 to the MVAPICH 2 DPU, and those are giving very good performance and scalability. Now, Tau, I think Samir indicated that yesterday, and today also he will go into much more details. I'm very proud again, Samir, to work together over the last several years. So the end community is really now able to take advantage of both MVAPICH 2 as well as the Tau to really do performance engineering. You run your application even blindly without knowing the source code. You should be able to identify where more time is being lost, whether then you need to do some application redesign or the MPI library is not performing well. So you get all those information and then come up with a better solution. We have been working with Broadcom for the last 2 years. Dr. Hemal Sai is sitting here. We have been working very nicely. So what we have done is like a 2.37. We have now an optimized version for Broadcom adapter, Rocky V2. Their system, so here you can see some of the numbers. Latency, we are comparing with OpenMPI. So this is like a 2.3. This, the red line is the 2.37x Broadcom. It will be pushed to the public release soon. But as you can see across the point-to-point and collectives, we are able to, in fact, beat. And there is a larger cluster, like a 64 node with the Rocky V2. We are able to get the best performance there. And those are the micro benchmarks, but these are actually the applications. So here you will see like a, this is like the CP2K, STO DFT LS version. This is a WRF, Konus 3 kilometer. This is a 12 kilometer. So as you can see, the red bar, we are able to actually give very good performance. So we have been able to optimize with the Rocky V2 adapters so that it gives very good performance compared to OpenMPI here. Similarly, like Dan mentioned about the Rockport networks, we worked with them earlier. We had a port for them. So this is already available in the 2.37 release. So if anybody is using Rockport, you should be able to use these. They also have, like we are able to deliver around like a 3 microsecond latency on that network. And then this is the earlier version of the Slingshot. That is the Rocky adapter basically below Slingshot 10, not 11. I'll come to 11 later on. And here also we provide the support, and you will see very good performance here, especially with like comparing also with the Craze MPI, which is their native. We are able to even give very good performance in terms of the latency and some of the collectives. As you can see here, this is like MPI all reduced. We have been able to give better performance, even the Craze MPG version. So that is the standard release which has been going on. But then, if some of you have been remembering, like over the last several years when we do the open mic session, people have been asking us saying, yeah, you have too many releases, so try to reduce those things, and we have actually taken those into account. So this is our new series, which we have started, MVAPICH 3.0B, and then I'll talk about here MVAPICH Plus a little bit later. But this is the three series, and that actually has the support now for both OFI and UCX. As some of you know, like these vendors are being now segregated, is a loose term, I'll say. They're being into these two camps. One is the UCX camp and then the OFI camp. So we actually provide the support for both of them. And so that any adapters which sits either below UCX or below OFI can now run over MVAPICH 2. And on top of that, we have our own designs also, which directly go to the verse and all. So here you see, this is like the Slingshot 11, which is being used on Frontier. That's the #1 system in the world. And with MVAPICH, you can get around 2 microsecond latency on that system. And I have actually some more numbers later on. And bandwidth-wise also, here you will see, like we are able to saturate the bandwidth on the Slingshot 11 around like 24 gigabytes per second and 42 gigabytes per second. Now, these are some of the numbers. We are working with Convergence Network also very closely. This is with their OPX, MVAPICH 2, OPX. This goes through the Wi-Fi. They expose their adapter through Wi-Fi. And here, if you see the latency, look at the number, 1.08 microsecond. On their adapter, we are able to deliver 1 microsecond. And then the more important things is here. So this is, so some of you know like the history of this Convergence Network. I mean, they have the PSM2 that already works with 2.37, but we also have the through Wi-Fi. We are going through this OPX, and since it is a 3.0 version, it is also based on the MP3. So we are able to cut down the number of instructions to send messages and also receive messages, and that is reflected here. You see, message rate gets improved significantly. So we are trying to really take the MPI layer to the very bottom of the adapter so that it is working very closely to the bare metal. And then this is again comparing to 2.37. This is like the 3.0. This is on the Infiniment adapter. Again, we are very much similar. Like as you can see, the 3.0 version is not losing any performance, rather trying to give you equal or better compared to the 237. So then, as we are moving into not just HPC, but very soon I'll introduce like how you can use MPI for big data, okay, or even Spark and all. So we started introducing a Java binding, because for some of these workload, you actually need Java support. So we have this MVAPICH 2-J. That is the Java binding for MVAPICH 2. So through that, actually, you can actually incorporate like any of the Java applications now can use MVAPICH. So here, this shows a detailed the stack kind of things, the Java binding, Java NIO, and then we link it with the Infiniment verbs and all these things. Many slides you will see. I have included the papers. So these papers have more details. And if you use these, our design, so here we are comparing like some performance, Java binding, let's say broadcast performance, and here you will see this is a nonlinear curve, but look at compared to MVAPICH to JRA and J buffers, we perform very significantly, like almost 1.5x better than OpenMPI's equivalent there. So then, as many of you know, like the cloud is getting a lot of importance, so we are also working very closely with all the different cloud providers. So in this context, I'll try to introduce. So we have the basic MVAPICH, but then we have an MVAPICH 2X. We call it an advanced version. So this has a lot of advanced supports, like from the Infiniment, like a UMR, ODP, direct connect transport, SARP, XPMM, and also this Infiniment network analysis and monitoring. I'll talk about that. So all those are packaged in our advanced version. And through that advanced version also, we created one for AWS. I'll talk about that. That actually runs natively over EFA adapter, because AWS doesn't use Infiniment. It has its own adapter. So here you can take a look at some of the things for the MVAPICH 2X. For example, this is like the derived data type. A lot of scientific applications use derived data types. So how efficiently you can actually implement directly taking data from different vectors, the structures, matrices, and we have these new designs. Here you can see like compared to Intel MPI, OpenMPI and all, we are able to significantly improve the performance. So those features are there in the MVAPICH 2X if you want to use those things. They are not in the basic MVAPICH 2 version. Now, we are working with the three cloud providers. As many of you know, the Azure. Azure basically uses Infiniment. Okay, they're HPC instances. So most of our things directly work. So not only the MVAPICH library, but also the library I'll introduce very soon, HiBD and IDL. So directly what happens once we make the release, the Azure team actually takes our releases, converts them into a CentOS image. Okay, so if you have an account on Azure, you should be able to directly use that version. Earlier, we used to make separate releases for them, but now it has been synchronized. And in fact, today afternoon, we have the talk from Jitin. He will be talking more about that. The AWS, as I indicated earlier, they use their own adapter called Elastic Fabrics adapter. So what we have done a, just like Verse, we have actually gone through the EFA adapter layer. Of course, they only expose that for other MPIs through OFI. They are in the OFI camp. So especially with our 3.0 version, you can also work with the EFA, but may not give the best performance. This is the release which gives the best performance because we are able to go directly work with the adapter. And these are some of the examples. As you can see, this is like a WRF code. This is mini AMR code. And here we are comparing MVAPICH to optimized with OpenMPI. And as you can see, like you can get as the system size scales, you'll be able to get like a 19%, 31% benefit if you use our AWS design. And this is a public release. So if you have an AWS account, you should be able to just download and run, and you should be able to see similar kind of benefits. Now, if you go to the Oracle, they have taken a little bit different paths. So they mostly go through the Rocky side. Okay. And so anyway, we support Rocky. So in that case, again, MVAPICH libraries together with the HiBD and all HiDL can actually work in a transparent manner. And here, if you see, I'm just trying to show one example of mini AMR. And here you will see, sometimes even here, compared to like HPCX and Intel MPI, we are able to even significantly reduce the application level execution performance. So those are on the CPU side. So let me move to the GPU side. I think yesterday Hari introduced, and I think many of you know the Kuda aware MPI concept. And we have been working on that concept. In fact, we introduced that work actually. Those of you remember, we had a joint collaboration between Mellanox. That time they were not part of NVIDIA and OSU. Mellanox and NVIDIA came up with the GPU Direct RDMA driver, and then we were able to put our MVAPICH 2 on top of that with the GDR copy and all. So that's what became Kuda aware MPI. And if you go back in the history, you'll see like a ISC 2011 paper. That was the first paper we published. And then since then, during the last 12 years, a lot of work, a lot of other MPI libraries, software libraries have moved to that. So this is what the MVAPICH 2 GDR supports, Kuda aware MPI, derived data type support. And I'll talk about this on-the-fly compression. In fact, Dan mentioned that compression, we have the solution already in the releases already for last 2 years. I'll go into more details. And then, of course, support for DGX. And we started with NVIDIA GPUs. Now we support AMD GPUs. Intel GPUs are actually being worked out. We have already things running in the lab. Here, actually, we'll have another. I think Casper will be talking a little bit more on tomorrow's. He'll give some talks on the Intel GPUs. And then I'll also be talking about a little bit Slingshot 10 and AMD GPUs, and then the Slingshot 11 for MVAPICH Plus. So here, if you see, this is the Kuda aware MPI. I think Hari showed that number yesterday in the MVAPICH tutorial. So if you do really, like if you have an adapter and the GPU device, so you can actually take the data from the GPU adapter through the adapter directly. So that's where you get very good performance, like a 1.85 microsecond. And this is from GPU of one node to the GPU of other node, not on the same node. Okay. So as you can see, like we are really able to deliver very good performance, and the bandwidth also significant improvement. Now, this is the last 2 years we have been working down on this on-the-fly compression. So the basic idea is that, and this is currently using GPU. We are in the process of exploring DPU technologies, but this is the GPU. So the idea is that GPUs are good for compression. GPU has a lot of cores, so you can actually do your main computation, but when the communication happens, can we also use that? Okay, so that is the thing what we have been exploring. So if I have a large data, and especially for these AI workloads, if I send the large data, it will take a big latency, and then bandwidth will be lower. But if I can compress and then send, based on the compression algorithms we use, the data size can be reduced, and then your latency reduces, and then you get very good boost in the performance. So we are working with Yifeng Kui from San Diego here. So he's one of the developer of the AWP ODC here. And here you can see, like you get, this is an application, seismic earthquake simulation application running on like a 512 GPUs. The application level, we are able to give the benefits. This is like the throughput in flops, higher is better, 18%, 35%. And then also the overall execution time, 26% and 15%. So this is like this was a best paper finalist in 2021. We have actually pushed that into the release. And in fact, tomorrow, Yifeng will give very nice results, very latest of their code they are using, and seeing, in fact, much more higher performance compared to these designs. So then this is the same compression also. So here you will see this is like all-to-all, many applications like all-to-all, which is very dense. And this is where we are using compression. And look at this is the deep speed. I think, Dan, you mentioned we already have, like if you are running with MVAPICH to GDR with compression, and the AI workloads can actually give you 36% benefit. So, so before you have the systems, we have the solutions. So as soon as you have the hardware, the solutions will run, okay? So similar things we are doing with AMD GPUs also. So this is, we have done not just for the NVIDIA GPUs, so this is for the AMD GPUs. This is the Broadcom aware thing. So as you can see here, within the node GPU to GPU, we are able to deliver like a 1.75 microsecond latency kind of things. And these are all other collectives. And as you can see, the numbers here, so here again, we are comparing MVAPICH to with OpenMPI with UCX. And we are able to, again, deliver better performance in the collectives. And this is with the Slingshot 10 plus the AMD GPUs, and similar kind of trends also hold good. And we have done comparison with OpenMPI and also Craze MPG. And many times also we win over. And these are also the pure RECL number. You know, just like the NVIDIA has nickel, AMD has RECL. So we are able to beat all their collective algorithms. So then we have this all the different versions, and if you remember, like especially those of you know Adam Moody, he couldn't come this year. He's from Livermore, so he has been actually asking us in some of these open mic sessions, saying, okay, reduce the number because it is becoming more difficult for people to deploy. So this is our MVAPICH Plus, we call. Okay, so moving forward, you will see there is a base version MVAPICH Plus, that's all. Okay, so the MVAPICH Plus will have all this advanced, like a GDR and MVAPICH to X, AWS, so those will all be combined. Okay, so in the end, you just have to work on 2 versions, not more than 2. And this is where various libraries are being merged into this release. So this will simplify the installation, and it will give you the best performance for all these architectures. So we already started on this. We have an alpha release, alpha 2 release we made last month. And this is again based on our MVAPICH 3. And this can actually now support for AMD, NVIDIA GPUs, as well as the MVAPICH enhanced GPU collectives. And then we'll have, so we are gradually bringing all those GDR copy, GDR IPC, all those features from the GDR to here. So these are very latest numbers. These are on the AMD GPUs. So this is from the 3.082. As you can see, like this is the, so let's take this one. This is our new release compared to like the previous one. So this is the GDR copy is being used. As you can see, we are able to reduce the latency here. And this is on the AMD GPU on a local system. And this is actually Tioga. That is the precursor to the El Capitan system on the Lawrence Livermore. So we are running things there. And here you can see, like we are able to give you very good performance. And still, we are trying to optimize this further. And this is the our collectives, as many of you know, as also Dan indicated, we spend a lot of time optimizing collectives because many of these HPC applications, Even the AI applications are very much dependent on the performance of the collectives. And we have been working on this for the last 22 years, optimizing continuous collective. We have actually a lot of intelligence there. In the code, it automatically, when the MPI library is getting launched, it automatically detects like the what architecture, the CPU, GPU, what network, and based on that, even for each, let's say, algorithm like a broadcast, if you go to our code, you will see 17 different algorithms, okay? So we spend a lot of time for different message size, systems different size, PPNs, actually come up with the best algorithm, and those are all embedded. So in fact, the next project which is being worked out, I may not talk here, using AI techniques there. So we are coming up with ML models for the collectives, okay? So that we don't have to spend a lot of tuning because we have so much data over the systems, architecture and all. So next time we can actually, within the MVAPICH library, there will be a module which is an AI-driven module. So that will actually detect the architecture, system, SSIs, and then say, okay, what algorithm to use. We are not completely there yet. Some papers are under review. We'll see once those papers get accepted, we'll try to bring those here. So that's why here you'll see this is the NVIDIA plus Infiniment. As you can see, like here we are able to give significant performance compared to like we call it like a XCCL, like whether NCCL or RCCL. Everybody has now an acronym, all the vendors. So we have actually taken inside MVAPICH, either we can run with that, or we can run with ours, or you can do a hybrid. Okay, so we have provided this runtime variables, and you can force, let's say with NICL, force with RECL, or leave it to the library, and the library will automatically decide the best performance or best selection of algorithm. So then moving forward, the same things also, this is the AMD GPU plus Slingshot 11. That's like the frontier system and the El Capitan system. So this is the MVAPICH Plus. As we are working out, as you can see, this is the blue is our MVAPICH Plus. GPU numbers, we are able to beat even all the recall things. So then let me move into this Converge software stack. I introduced this overall idea, of this cycle where the convergence is taking place. So we started with this HPC, but gradually we are trying to move into this domain, okay? Using the same as an MVAPICH as the substrate. So I'll talk very briefly about how do we support deep learning, machine learning, big data, and data science. So we have actually releases based on these. So what we have done in the deep learning side, so we call it like an MPI Driven Infrastructure. So if you take a look at the Horobo, touch distributed, deep speed, and Dan also mentioned that many of them are using like the underlying library. So we have actually linked it. So we have a library called, the project called HiDL. Many of the students are working there. So now you can actually, we link it our MVAPICH to GDR or MVAPICH to X so that you can do CPU-based deep learning or GPU-based deep learning. So now if I show you some numbers, so here you will see like this is a HiDL software stack release 1.0 we made, I believe, several months back. So as you can see here, so this is the NVIDIA GPUs, and the red, so this is the higher is better. So we are able to beat nickel a little bit here, but we are able to equal or better, as you can see. And AMD GPUs, significant benefits we are able to give compared to that, their RecordBased solution. And that is not only on the small scale, on the large scale, like these are the numbers we took few years back on Summit. As you can see, it is scaling to 1,500 GPUs. Similar things are happening on the CPU-based. These are the TAC Frontera, 2,000 nodes. You can actually run, this is the TensorFlow running, delivering like a total training. We are able to do it in 7 minutes. A lot of people say that you only need to use GPU systems, but if like a TAC Frontera and all has this large number of CPU nodes, you can actually run your deep learning applications there also. So we have enabled that. So similar things we are doing with the machine learning. With the machine learning, there is a package called CUML. So what we have done is, like we have introduced that MPI for Pi, and we have linked it with our MVAPICH to GDR. So all your machine learning applications can now take advantage of our MVAPICH library. You don't need anything else. If you are doing k-means, linear regression, nearest neighbor, and see the benefits. We are comparing with NICL. Compared to NICL, this is our libraries, as you can see, it can give you almost like a 1.6x, 1.35x improvement, okay? Because if you remember, like the bottom line is the collectives. If you can optimize collectives, you get the better performance, and that is the path we are taking. Our MVAPICH library, we are trying to completely optimize the collective, so that gets reflected into these other libraries. The same thing now we have done the big data. As many of you know, we also had a high BD project, which has been running on from many years. Like we had a native design for Spark, Hadoop, Memcached, all those things. We did it with the native Infiniment. But then the question somebody asks, okay, can I run your stack on Slingshot 11? Then the answer is yes, theoretically okay, but we have to work on that, okay? So instead of doing like per network, so what we are doing in this figure, so if you see earlier we had a RDMA Spark over UCR over Infiniment and Burst, that was only available for Infiniment and Rocky. But now if we put it through MVAPICH to J, as we discussed earlier, and our MVAPICH to library, now we can actually support any network. Okay, so this is the motivation of the MPI for Spark. Okay, and then we have made this release, and as you can see here, some of the numbers. So here we are showing like a Infiniment, this is Omnipath, the same stack runs. We don't have to redesign it. Okay, because since the MPI library is running over all different networks, and as long as we can run the Spark or MPI, it is a performance portable. So tomorrow any new network comes, as long as the MVAPICH has that support, all the stacks will start running. And then here you see, it is able to deliver even better performance, of course, on the Apache Spark. Even compared to our RDMA Spark, it delivers better performance because RDMA Spark has been a few years older design, so we have not brought all the features. But on the MPI layer, we are continuously taking advantage of the network features. The same thing we are also trying to do with the new data science community. Some of you know they are using something called a Dask. So now we have an MPI for Dask. Okay, so here the Dask has this support TCP or UCX. Now we introduce this MPI for Dask, MPI for Pi, and linked it with MVAPICH to either CPU side or GPU side. And these are the numbers running on the Cambridge Wilkes 3 system. And then here you can see, compared to IP over IP, of course, we win. This is the UCX, and look at these numbers. This is the latency, the lower is better. We are able to deliver better performance, like almost factor of 5, factor of like a 27%, and in this side is like a 7x, 8x improvement. So that means now if you have any data science applications, just install our library, and then that's all. You will be able to get the benefits, and this is also on the NumPy area slicing benchmark on the TAC Frontera. You see almost 1.26 as or 3 factor 3x. So then moving forward, as many of you know, this OSU Micro Benchmark started almost from 2004. It is continuously happening. Every time we make a release or some new features comes, we include that in the OMB. We had the initial in the MPI, PGAS, and these days, many of you will be seeing that a lot of procurement actually have those lines kind of here. So the OSU Micro Benchmarks numbers. So recently we made a release, MVAPICH to 7.2. Yesterday we had the tutorial on this. I'm just highlighting, so this has now support for MPI4 session, neighborhood collectives, persistent communication, even PAPI support, and also graphing support. So a lot of these tools we are allowing, so people can actually do quick performance evaluation on all these modern interconnects. So then we also have this project, which is linked here, which is the Infiniment Network Analysis and Monitoring. We call it Inam. So it actually is one of the very unique tool which actually takes, sorry, there was a picture here. So it actually takes from the applications to, it's a pure introspection. So from the top level applications to the scheduler to the MPI library, it actually can show you how the packets are moving. Okay, you get a lot of statistics. You can quickly identify the congestion in the network, and you can link it with which application is trying to create that. So we are working with a lot of supercomputing centers. They have deployed this. And you can get like from a top to bottom analysis here. And this is we released this 1.0 release last year. It has a lot of features. And then while we are going on, we also have been spending a lot of time on the application best practices. So as some of you know, like in the end, that's what matters. A lot of people want to run the applications out of the box and want to get the best performance. So we have a best of practice pages. So if you go there, we have contributions also, not just from our group, from other groups. So we put them, give the credits to those people. So if somebody else is trying to run these applications, they just have to refer to our page. Okay? And here I'll try to highlight some of the things. So this is like a GROMAX application, actually working with Tau performance engineering tool. And this is like MVAPICH to on optimize. So here we see that like MVAPICH on optimized, this is optimized, and we are comparing with OpenMPI plus UCX. So in fact, this is on the Broadcom cluster we are running. See what we discovered, like there is some parameter, like there is a hybrid mode. You need to adjust the thresholds properly, okay, when you run. Very simple as that, okay? But it still takes several weeks for you to find out where you are losing the performance. And if you change that, you see you get 2.5x improvement kind of thing. So that is the kind of directions when we are going. So now with that, let me quickly move into some of the upcoming features. This is our kind of a roadmap, and I'll go into quickly over this. I talked about this is the MVAPICH 3.0 and MVAPICH Plus series. So gradually in the next few months, what we want to do, our 3.0 will have a superset features compared to 2.37. Okay, so that will be the first thing, so that the 2.37 will retire and then move into the MVAPICH 3. That will be the production code. And then, as you know, the MPI 4 standard has been introduced, so then we'll start adding the MPI 4 features. And then the MVAPICH Plus, similar kind of things. We have already integrating the 237 and MVAPICH 2X. And currently we have support for NVIDIA and AMD, so we'll make it like a feature rich compared to the older releases, so that all the users can move there. And then we'll have the support for the Intel GPUs, and we'll also have support for some accelerators. I'll try to mention about that in the next slide. So as many of you know, a lot of new kind of AI accelerators are coming, okay? Like a Havana Gold, which is deployed at San Diego. There is a Cerebras. So like this, a lot of chips are coming. Currently, they are coming from the AI side, okay? You can only run AI workload there, okay? You cannot run any HPC workload. So we asked the question saying, okay, why can't we even allow that HPC workloads to run? So what we have done, this is on the Havana Gold system. Chenchun presented this results yesterday, and I think Mahidhar will talk a little bit about that in tomorrow's. So this is on the SCSS system on Havana Gold. You can run MPI jobs, okay? So, and here, especially if you see, like this is the this is the pure Havana, call it SCCL. You know, everybody is following that XCCL. This is the Havana Collective Communication Library, and now you can see this is our through MPI, and we are able to give you like this is a 4 nodes, 32 HPUs. We are able to do equal or better from the HPC applications. The only thing is lacking there, and I think we have discussed with some of you, how you can actually write a kernel for the HPC application on those hardware. If that is allowed, you can actually run HPL on this or any of the scientific application, because we have the MPI library ready from the communication side. As long as you take care of the computation side, then people can use these machines for both AI workload, even big data workload, everything you can run on these systems. So then we are moving into the next phase, which is the FPGAs. As you know, there is a lot of interest in the recent years for FPGAs. So now we have an MVAPICH for FPGA. Yesterday, Nick Contini presented some of these results. So we are trying to bring the same CUDA-aware concept to the FPGA. Just like how you can move data very efficiently from device to device using your PCI interface. So that's what we have started doing. We were PCI, FPGAs to FPGAs. And here, in fact, we are also working very closely with ETRI. We have some visitors from ETRI. We are working jointly with them. They are designing some good hardware. You will see those solutions will be coming out very soon, not only for their devices, but for other FPGA devices here. So then going to the Inam, I talked about the Inam also. We are continuously enhancing. So there is as you know, the Inam has a database. So continuously we are trying to improve the performance on the database, because as the system size scales, the overall performance, how the user can interact is based on that database performance. So here we'll be trying to provide a lot of the more number of users, then add support. We are trying to, even though the Inam stands for Infiniment, but now we are expanding the support for Ethernet also. So through SNMP, so in the same tools you can use for both the clusters and improving on some of the deployment and all. So then moving into the high performance deep learning, I mentioned about the high-DL stack, but that is only for data parallelism, okay? But as you know, the field is expanding quite a lot. As the model sizes are increasing, you cannot fit them into a single GPU. So this is where we have been doing a lot of research on different kind of parallelism. And we have a new release coming out called, instead of saying a high DL, we call MPI for DL. Okay, so that is a much more easier to remember, MPI for DL, MPI for Spark, MPI for Dask. And here we support actually all these parallelism, layer, pipeline, spatial layer, spatial pipeline kind of things, and currently is available for the AMOVANet. These are some of the sample numbers. Yesterday we presented some of the details in the tutorial yesterday. So this is the new release. We are trying to target before Merck, but we couldn't do it. Might be next week you'll see this release. So then for the Spark side, we also have I showed you some initial numbers, sorry. This is the MPI Spark release V2, which is coming here. So as many of you know, the Spark and all these stacks run with a resource manager called Yarn. We didn't have that support earlier, so this is where we are trying to bring the Yarn support so that your applications, whatever you are running with the Spark, can very nicely get moved to our MPI for Spark and can run on any of the networks. You mentioned Slingshot, Infiniment, Rockport, Cornelis, Omnipath, you name it, it'll try to run on that system, so you don't have to invest a lot on those software stack. And finally, I think what we had a talk yesterday from Poya. Gradually, as you know, there are a lot of users are trying to, let's say you have an Amazon cluster instance, okay? You spend some time to actually configure it with all your, let's say you want to run NAS parallel benchmarks or something on a 5 node or 16 nodes. Can we do it AI driven? Okay, so that's the conversational AI interface we are trying to provide. So instead of you sitting down through a lot of scripts and all, can you automatically, like before going to bed, you said, okay, run this task for me. And that's the entire framework we are trying to design. Okay, so it brings the AI tools, it brings an HPC knowledge graph. Instead of you sitting in front of the computer and trying to do all those scripts and all, running this, your system will be able to run that for you and have the results tomorrow morning, okay? The only thing I know that you can then combine with your ChatGPT to write papers, okay? So you should be able to very rightly, high throughput paper writing. That's what is going to happen. So with this, let me conclude this. So as you saw, we are working on a lot of projects, but they are all related. We are trying to enable the HPC, AI, and big data field. But I'm very proud. I mean, these are not only individual components. I know, Dan, you mentioned like 7 billion hours, all right? You people are providing. This is similar to, you know, the McDonald's says every time I see that number, the McDonald's in the world, how many burgers they have sold. Those old days, they used to, then I remember Dan's number saying, okay, so many burgers, so many MPI jobs are running there, kind of things. But that is, we are trying to make impact. Many people may not be knowing, the end application scientists may not be knowing that they're using MVAPICH under the hood, but we are enabling the progress of the science. And I'd like to highlight 2 of these things. You might have heard of this in the news, NASA's DART mission. Last year, when you saw the news, this actually has come through Lawrence Livermore scientists, and we have been working with Lawrence Livermore very closely for, again, I think last 10 to 12 years. So they use MVAPICH on most of their missions. So in an indirect manner, actually MVAPICH is helping the NASA's, all these kind of the interplanetary project, and the other project, which is the nuclear fusion. Okay, that also is making a big impact. You heard about that in December 2022. And again, I'm very proud that we are enabling these scientists to really go into the next phase, which will try to solve the world's problems. And then in order to solve that world's problem, this is again the chart I want to mention. So we are no longer just the MPI group, primarily MPI, but we are able to now handle all the different kind of a workload. So if you have any complicated workflow, machine learning, deep learning, big data, we have the solutions for you. So with this, I'd like to close this presentation. These are all our sponsors. Without their help, it would not have been possible to work for so many years. But more importantly, these are all my heroes. So every slide, whenever I present, I salute to all of them. For 22 years, a lot of these student staffs, they have worked, they have graduated, they are working at many other places. Many of you are here. So everybody comes, contributes something, and then goes. So with this, I'll close the presentation here. And if anybody has quick questions, I'll be happy to answer. Thank you. Any questions? Locally, or I know I'm eating into your break time. Any online questions? Okay. Yeah. Yeah. Please, let's just hold on to the microphone.
Okay, it seems like I have a sort of a bad habit, liking no questions for any sessions. So that's bad for me. I would like to learn more about your thought on the UCX, because I think it's mostly the Oak Ridge guys who are driving this UCX effort. But again, what is your thought on the UCX moving forward, whether there is a good option for the UCX to be integrated with the MVAPICH, or should they have a separate path for the longer period?
Yeah, so UCX, just to clarify, I think it's a consortium again. I know we have NVIDIA people here. I also sit on the UCX board. So we have actually, as I indicated, our MVAPICH Plus has that UCX support. Okay, not the older release, but the newer release. So these are the two camps which have formed, the UCX and then the Wi-Fi. So now we are able to support both. Okay, how the UCX will move future, I don't know. Okay. It's a kind of a consortium with NVIDIA, different national labs. They are involved. So at this time, we just want to provide that support, and we get good performance. So our objective, because we sit a little bit up, and also for some of the numbers, what I showed, MPI for Spark, MPI for Dask, we actually beat UCX. Okay, those are our native designs. Okay. So we are supporting both. Either you can go through UCX path and get whatever performance you would like to have, or you go through our design and then get even equal or better performance.
A layer.
Yes, yes. So the UCX is, you can talk to our NVIDIA colleagues here. They're trying to abstract the network, the features, and then bring it to the UCX layer, so the upper layers can only interact with the UCX. Okay. But then what we have seen, I mean, this is always happens in the the software abstraction. If you go to the upper level, you can quickly have a design, but you don't have control. If I want to optimize something, you are dependent on what, let's say, UCX provides. Okay. Whereas if we go down, which we have done over the last 22 years, I mean, we know that network adapter. Okay. What we have the features, so then we might be able to optimize it in fact better, and that's what some of those things what I showed.
Okay, I think that may be sort of the limitation on the UCX side.
Yeah, I'll be happy to have a discussion with you, Hemal. Yeah.
So I was going to ask a question on the consolidation, but you already answered. I think it's a good idea. My question is different. With having only two, MVAPICH 2 and MVAPICH 2 Plus is a good thing. What is the plan for migrating the existing users of all these different libraries which were optimized for specific architecture?
Yeah, so the idea is that we will have MVAPICH and MVAPICH Plus, but then all these other IDL, the Spark, UCX, and all can run on any of these. Okay, that is the plan. Like as we are moving the MPI level, we'll have two versions, but the upper versions will be available for both. But of course, the MVAPICH Plus will have more features, more scalability, performance kind of things. And as you know, that MVAPICH Plus is a little bit closed. Okay, because we want to protect the thesis, work of the students kind of things. The basic MVAP is open kind of things.
Yeah, my question was more like, if I'm using MVAPICH to AWS today,
yeah,
what is the migration path? And then others, all of them to move to MVAPICH 2
So that is the word
Plus.
I think I indicated in one of the things. So gradually it will take us a few months to bring all these features in. And then once it is the MVAPICH Plus is the feature superset features, that's what I refer to in that slide, then we'll deprecate those older versions, so that then we'll ask all the users to move to our MVAPICH Plus. For some time, we'll have both of these available, but we'll give some time, and then so that once the people move to the newer ones, then we can focus more on those directions. Any other questions? Sure.
What do you think of RISC-V, and do you expect to see designs with good networking support for big data and HPC, maybe even hardware, software co-design? And that's from Benson.
Okay, so that is a great question. So I didn't go into more details. I mean, currently, again, as you saw in my very original slide, we are monitoring the growth, not only in the networking technology and the progress in the CPU technologies and all. So the next one is, of course, as you heard, the many machines will be deploying the Grace, Hopper, those kind of systems. And we already have support for ARM. We worked with ARM people, MVAPICH supports ARM. You can actually directly out of the box, it can run. But we need to optimize those for the Grace. And similarly on the Hopper GPUs, as of now, we don't have access. As soon as you get the access, we'll be able to optimize on that. So then, as you know, behind the scene, the RISC-V and all those things are coming up. But I have not seen any real deployments yet on the HPC side. But once those come in, we'll be very happy to even move to that system. So the answer is yes, we'll be able to support those things as the market catches on to those newer architectures. Okay, and in the past, we also did the same thing for power. Power architecture, if you remember the summit results I showed, that is the IBM power machine. We optimized for power, and then MVAPICH supports runs on all those machines. Okay, so I think we are running a little bit late into the breaks. Let's take a short break, might be a 10 minutes break. Coffee and all are there. So then we'll start with Gilad's talk at 10:45. Thank you.